Hello, good morning. I think we're ready to start Nikolay's Babakov doctoral meeting entitled Explainable AI and Bayesian Networks Development, Explanation, and Real-World Application Insights. So Nikolay has extensive academic background, holding master degree in natural language processing by Higher School of Economics in Moscow. He also has gained some very valuable experience as a research engineer in Skolkovo Science Institute. So Nikolay currently focuses on explainable AI, and his academic trajectory and research trajectory focuses on natural language explanations of Bayesian networks. So welcome, Nikolay, whenever you're ready.
Okay, thank you for coming to my doctoral meeting. Today I will present you with two of my papers that will most likely form the core of my thesis. Okay, so yeah, the first one is actually dedicated to the core of the whole PhD program of mine, which is explanation of Bayesian networks in natural language. But before we start, maybe not everyone has deep knowledge of Bayesian networks, so let's just have a quick quick overview of what a Bayesian network actually is. So it is a probabilistic graphical model which consists of nodes that represent a variable which can be either discrete or continuous. So in this case, we can see the Bayesian network of binary variable nodes. Yeah, and these nodes are connected to each other with the edges, and the edges actually encode the causal connection. For example, here we can see that the fact of some abstractive patient travel to the world may increase or decrease the likelihood of having that tuberculosis. So yeah, in principle, it is a directed acyclic graph. And what is most important here is that each node has a corresponding so-called conditional probability table, which actually encode the probabilistic relations between different nodes. So what can we do with Bayesian network? We can actually ask it any questions, like for example, how will the probability of one node changes if we know something for certain about the other node? Let's have a closer look into some examples. For example, in this particular slide, we say that okay, we know that patient smokes. So how it changes the likelihood of having lung cancer? And yeah, surprise, surprise. Here, without any evidence, we can see that the likelihood of lung cancer is like 5.5%, and if patient smokes, it increases almost 2 times. Yes, so we in this case we can see that this is like the reason, and it updates the likelihood of so-called child node. But actually, the probability updates could be distributed within any direction in case of Bayesian network. For example, in this slide, we can see that if we provide the evidence about the patient having dyspnea, consequently updates all the probability of the parent, so-called parents node. Yeah. So, what is the idea of the first paper I'm going to present? Yeah. Going back to this slide, we can have an intuition. For example, if imagine we are some kind of medical practitioner who wants to know how exactly, how and why the probability of patient smoking is updated if we only have the evidence of the patient having the dyspnea. So, of course, this particular Bayesian network is pretty toy one, but it is good for demonstration. But if the network is much bigger, it can be much more difficult to understand what are the exact paths of probability updates. That is why we present our original method for explanation of Bayesian network inference. The background of this method goes back to the fact that the Bayesian network could be presented as a so-called factor graph. So normally when the Bayesian network is presented in factor graph, it is undirected, meaning that these edges stop having any direction, unlike its original form in standard Bayesian network representation. But for our aims to explain the particular paths of probability update, we actually encode the direction into the factor graph, and these directions lead us from the evidence nodes to the target node. It's just a short reminder, evidence and nodes is what we know about, for example, the patient, and target node is the variable we are interested in. Yeah. So the next slides will be about the intuition of the calculation of this factor arguments and how they should be verbalized. So the first thing is that just to visualize it better, the factor it is actually the function which corresponds to the conditional probability table, but the useful property of the factors is that we can perform different operations with factors such as multiplication, marginalization, division, normalization, etc. So using these operations, we can actually calculate the numerical effect of a particular evidence node having to the consequent target node. So, well, this is a general intuition of the calculation of only one step within the factor argument. So, yeah, as I said, we can use multiplication and normalization and marginalization of a factor. So the idea here is that within this step, we have this factor which actually encodes the probability, possible probability updates with respect to all possible evidences. And yeah, we perform several operations according to the evidence we have. And in the end of these operations, we arrive to the so-called step effect, which actually encodes and numerically encodes how this particular evidence affected this particular target node. So now we have defined the step effect, and the intuition of the step effect could be applied to the whole factor argument. By factor argument, we mean the whole path of probability update from evidence node to the target node. So using the idea visualized on the previous slide, we may calculate the update of all factor argument from all evidence nodes to the target node, and in the end we get so-called factor argument effect. The good intuition that can be obtained from this slide is that if we, for example, imagine that we do not have this particular evidence in our factor argument, only the probability update only from this particular node we will be passed to the target node. Whereas if we have additional evidence, the calculation of step effect within this step will be slightly altered, and that is why different factor arguments will possibly result in different factor argument effect. And this concept of different factor argument effect actually the crucial in our further verbalization scheme. So why it is crucial is that obviously there could be different several paths between evidence node and target node, like for example in this case. Yeah, this node could be connected to the target node either using this complex complex subgraph on the left side, or using two separate factor arguments. And to understand how exactly we should present this particular path to the user of the Bayesian network, we first calculate the joint factor argument effect of both of these paths, and we also calculate the factor argument effect of these paths separately. Then we check whether the product of these two separate factor argument effects is approximately equal to the joint to the factor argument effect of the joint paths. If actually the product is approximately equal, then we present this separately. Otherwise, we present it jointly. So this was just probably not very interesting technical background, but the probably more intuitive part will be now. We can invent whatever method of explanation of Bayesian network we like, and we may believe that it is useful. And actually, unfortunately, this is what is done by many authors. They simply present explanation method without showing it to any potential users, and most papers end in this point. We have tried to go further, and we applied the human evaluation study. The human evaluation study incorporated like three alternative methods of explanations. First one was simply evaluation, was simply a baseline, meaning that we do not provide any kind of information about any intermediate updates of the probabilities within the Bayesian network. We simply say that, okay, we know something, and this somehow updates the probability in the target node. So no more information. This is just a verbalization of what we can see in the Bayesian network. Alternative method, which actually, of course, works better than the baseline, was obtained from another paper. And yeah, the idea of this method was to like verbalize what factors support the change in the target node, and which factors contradict the like the change of the target node. And yeah, and the third method was actually our method. So we performed a human evaluation study, and yeah, thanks to most CiTIUS students, some of the participants are actually sitting here. So thanks to them, I collected more than 20 valuable like pieces of feedback, and it showed that our method is actually better in terms of perception by human users. In particular, we asked about the easiness to follow the explanation and the understandability of the explanation, which is sometimes referred to as a mental model. And we also asked the participants to choose which precise method would they prefer if they have to choose. And from this plot, we can see that our method is most frequently chosen by the participants. Yes, so this is generally it. This is the outline of the first paper. If you have any particular question about it, you can ask now, probably. Otherwise, I can go on with the second paper. No? Okay. So this paper, the previous paper generally proposes the methodology, original methodology of Bayesian network explanation. In the second paper, we actually do not propose any original method, but we study certain properties of real medical practitioners' perception of explainability of existing AI models. So the subject of our study was so-called non-alcoholic steatohepatitis, or non-alcoholic fatty liver disease. And actually, what is the idea? The most precise method of diagnostics of this fatty liver disease is histology, which is namely taking the needle and using the needle, you namely take the slice of the liver, and you then have to take a look at the slice under the microscope. So it is the most precise way of diagnostics of fatty liver disease. But the problem is that there really is some kind of chance of person dying after that. So it is not very well, you should have a very good reason to ask someone to do that just to check. So that is why there are a lot of papers that have actually addressed the issue of non-invasive method of machine learning driven prediction of this disease. And the papers I performed comparison with rely on tabular data, and actually my work also relied on tabular data. But the significant difference between the paper I prepared and the existing papers are first that I made the model available, which is actually rarely the case in such papers and in most of medical papers. And the second thing is that I ran the user study with real world medical practitioners. So there were two research questions. The first one was that whether the transparency of a model increases the acceptability of model by medical practitioners, and whether the explanation at all increases this acceptability. So to train the model, I obtained data from National Institute of Diabetes and Digestive and Kidney Diseases. And actually, this was probably the most complex data I have ever worked with. Normally, if you go to Kaggle and download some stuff, it is just one table, and you are happy to train your model. But in this case, it was not like that. It was 17 CSV files, and each file corresponded to a particular form filled by either patient or medical practitioner. So in my case, the most important one was this histology review. From this histology review was actually the result of the reviews of this dangerous procedure when you take the slice of your liver. I took only my target variable from this form, just the results of the decision of the medical practitioners, whether or not the patient has this fatty liver disease. But my features I used to train the model were obtained from other tables, so which corresponds to the non-invasive prediction of this fatty liver disease. Well, this is just the list of features. I believe most of them could not be understood by many of us, but this is not the point. The point is that this is actually the good insight I obtained from this study, is that if you develop some system that is supposed to be used by real-world medical or whatever other practitioners, you should work in a close collaboration with this with a specialist, because originally I used the features for training this model proposed in different paper, but when we first presented the model trained on other features, our small group of medical practitioners indicated that some features did not make any sense and other sensible features are missing. So by several rounds of iterative improving of the features to be used for prediction and for demonstration to the medical practitioners, we ended up with this set of features. Now I will show you how exactly we demonstrated the explanation of the model to the medical practitioners. The first part of explanation interface consists of actually the features of the patients, like the information of the patient. What should be taken into account here is that one part of the table simply corresponds to the features that I have shown on this slide. So actually these are the features really used to the prediction. But the special thing about medical data is that we cannot simply take all the data and use it blindly for training the model. Before it, we should apply certain inclusion and exclusion criteria to the patient, so they meet the requirements to our cohort, like we are interested in. But the problem is we do know that this kind of inclusion and exclusion have been performed, but the medical practitioners that look at this prediction, they do not have information about it. That is why, apart from showing the actual features used for the predictions, we also showed the general information about the inclusion and exclusion criteria applied to this patient. After that, we showed the decision plot, like from SHAP. Etri may know it very well. Yeah, and yeah, but probably it can be supposed intuitive, but in fact it isn't, because, well, especially for medical practitioners who do not have any idea about machine learning and stuff. So that is why the third and the final part of our explanation was a textual explanation. And actually the experiments of our human study involved so-called black box models and decision trees. Black box models is generally everything like neural networks, random forest. In our case, we use the random forest. So the idea is that the way of verbalization of prediction varies according to the type of the model. In case of black box model, we can do nothing else but listing the variables that actually increased the in this case increased the risk of this disease, and simply list the variables that decreased the list of the risk of this disease. So the idea of whether a particular feature increases or decreases the risk is directly obtained from SHAP values. Yeah. In case of decision trees, we also incorporated the SHAP values, but also we used like the beauty of transparency. So namely we verbalize the paths or this like decision paths within the decision tree. To be more precise, we can have a look at this slide. So here, for example, we see that this is the value of this feature, 6.9. So within the decision path, we go here. It is less or equal than 7, and then it is greater than 4. So in the end, we say that, okay, greater than 4 and less than 7. In the same time, like this feature equals 0.9. So we within our decision path, we passed the like less than 1.7 and 1.2. And in the end, we verbalize that, okay, this is less than 1.2. So yeah, if we, the idea is that if we did it straightforward, we could have told that, okay, it is less than 1.7 and 1.2, but for the end user, it wouldn't had much sense. That is why we performed certain pre-processing to make the verbalization of decision paths more sensible. So this is just the outline of the metrics. At the end, we random forest performed best of all. Still, the metrics are not perfect, but strictly speaking, we had only like less than 1,000 samples, so it was predictable. And yeah, decision tree performed much worse. Yeah, but it has the property of transparency. So the biggest intrigue of our of this particular work was whether it makes sense to has the smallest metrics, in this case of decision tree, but to have the explanation more transparent. So let's check what was the answer. This is actually slightly complex plot, but I will try to briefly explain you the idea. What I did is that I took the I trained the decision tree on a train split of data. I took the test split of data. I ran the prediction, and I generated the explanations of the corresponding predictions on the test data. And each small plot corresponds to the fact that during the explained prediction, we referred to the certain threshold of the certain feature. So, for example, this point corresponds to the fact that during the verbalization, we told that because HbA1c is greater than 5 point something. And I collected such statistics for all features I used for training my model. And what kind of insight we can get from here? The plot corresponds to the common knowledge of medical practitioners of what is actually the normal range or normal threshold of each particular feature. For example, the most intuitive one could be like BMI. Everyone knows that BMI should be no more than 25. Yeah, and here we can see that during the explanations, the decision tree actually very often referred to this sensible threshold. And it is also true for several other features. For example, total cholesterol, where we know that the normal range is between this 130 and 200. And during the explanations, the decision tree explanation referred to this 200. So its reasoning made sense from medical point of view. In the same time, we can see that this is true not for all features. Like, for example, let's say this particular type of cholesterol has some strange references. Total protein is also somewhere in the sky, so it does not make much sense. So the first insight is that not this thresholds engaged in the decision tree explanation, like, not always make sense. Then we simply run the human evaluation study on real medical practitioners, whereas the human study in the first paper was performed with just you guys and my friends, etc. This particular study was run with real medical practitioners, and we have seen that there actually no any significant difference within like 5 properties of perception of this explanation by decision trees and random forests. So our conclusion from, at least in this particular setup, was that it is better to use the random forest or any other black box model which performs better, and there is no much sense in sacrificing the metrics. Yeah, so this is it.
Your fascinating presentation. So we are now opening the question turn. So if anyone has any questions, please welcome.
Nikolay, for the second problem, did you try Bayesian networks or why?
Yeah, this was my original plan, but they simply did not. I failed to train them properly, and actually, as I said, it was like 600 something samples. So yeah, it was not enough to create a proper structure of Bayesian network. And yeah, we also tried to create the structure by ourselves. I mean, by my medical colleague. But yeah, finally the data was not enough to train the proper Bayesian network. Yeah, so but originally, of course, I wanted to use it for explanations. But yeah, in the end, we want we want to have the problem solved, right? Not to have it solved, but certain tool. Yeah, I dropped them just in this point. Yeah, even though the metrics are more or less comparable to decision trees, the structure, even I understood that the structure of Bayesian network did not make much sense. So that is why I simply decided to reside to solving the task itself rather than concentrating on particular AI model.
Nikolay, could you come back to your slide of your first paper of human evaluation? You said that, well, our mates from CiTIUS participated in this experiment. So I was wondering, is there any kind of a criteria or well, some kind of metric that you were following to, to choose the people who were participating in the experiments?
Well, originally it was just the idea of English speaking and having something to do with computer science. Yeah, but afterwards I understood that I could have placed certain understandability test before the person proceeds to the evaluation itself, because a good decision was to leave after each case. I left the free text field to make any comments, and certain comments from 2 or 3 participants made me understand that they actually did not get the idea of Bayesian network at all. Like, for example, I remember one funny thing. For example, one participant asked, when you say that smoker 50% and non-smoker 50%, what do you mean? Does it mean that you occasionally smoke, or what is it? Whereas actually it means that, well, we know nothing, but according to our preliminary knowledge, the person can be smoker with 50% chance. So having a look at such comment, I understood that the insights collected from these participants are not valuable, so I simply dropped it. Yeah. So yeah, it was like mostly it was a combination of my preliminary knowledge about the person and like the post filtering of the results. Yeah, this was the idea.
Okay, so basically you use some kind of a formula, something like that to well achieve the responses from your participants, which were like open questions, right?
No, they had yeah, for example, this easiness to follow and understandability is collected using Likert scale by from 1 to 5. Yeah, but a part of that, they also had the option to write any comments, and this is actually a very good practice, just because you cannot foresee all the things, all the ideas they get during the participation.
It's about your data sets. The data that you achieved from this page basically, were they really complicated to get and more complicated to synthesize?
Synthesize. Okay. Yeah, actually, it was the whole new world for me, this medical data, because as I said, I'm used to just downloading some kind of, well, I have a background in NLP, so yeah, you just download the data set from whatever source and you're happy. Here it is totally different. You should, even before proceeding to it, you should already have some kind of draft of your potential paper. You should write the motivation, like why do you need this data? What is your hypothesis? What are you going to do with it? And then you should get the ethical approval from the university. Fortunately, our university was pretty fast in that. I expected it would be much longer, but it was resolved within like less than 1 month. So yeah, from the moment of start to the moment of obtaining the data, it passed like 2, 3, or maybe more months. Yeah, so it was complicated. Yeah, it actually, as I said, this is a complex data, so you should do something similar to like a SQL join operation, and after this is the first thing. So actually, each patient can correspond to several fixed-sized samples in the final data set. This is the one thing. Another thing is that you should select the features, and yeah, I described the feature selection process. It was pretty complicated. It should correspond to the like medical practitioner knowledge. Yeah, so this was generally it. Yeah, but in the end, I should get like general type fixed size samples. So yeah. Mm-hmm. Okay. Okay.
Okay, so maybe if, well, I mean, people from the chat or from the teams, if they have any questions, well, you're welcome to ask. Anyway, Nikolay, that was fascinating presentation. Thank you so much again. And I think we're going to close it here. Thank you.
Thank you. Thank you.